So we've talked about how function transformations work. We know that this first one, this looks just like square root of x, but we shifted it right 3 and up 5. And this second equation looks just like absolute value of x, but we shifted it left 4 and down 1. So we know when we add or subtract inside or outside the functions, it shifts it up and down, left and right. If it's inside the function, it's left and right. If it's outside, it's up and down. What we haven't talked about is what if we multiply? If we multiply, instead of shifting it, it stretches it. It forms a dilation. I'll tell you what transformations happen to these, and then you can kind of be like, oh, okay, I get it. Just like with adding and subtracting, when it's on the outside, it happens in the vertical direction. These first two ones are vertical stretches, or vertical dilations. First one's a vertical stretch by a factor of 2. The graph normally looks like this for square root of x, where it has the point 4, 2. But now we stretched it, so now it's going to look twice as tall. So it'll now have the point 4, 4. The point is twice as high up. The second one is a vertical compression. I don't really care about the word stretch or compression or dilation as long as you're able to tell me it got taller, it got shorter. Compression by 1/2. This one now, instead of our normal square root graph with the point 4, 2, it now is going to look half as tall, where it only has the point 4, 1. You might be able to guess that inside the function, multiplying does a horizontal stretch or compression. One here is a horizontal compression by 2, horizontal. I have an issue with how I'm writing this, but I'm writing it purposely to point that out. What does that mean? Compression by 2, compression by 1/2? Does that mean it's getting skinnier or fatter? I don't like wording it like that because it's not clear. So I almost prefer, instead of using the fancy word compression, in this one just say skinnier. In this one you just say fatter. I don't care. 2 versus 1/2. Tell me if it's skinnier or fatter. And I mean, make sure you say 2 or 1/2. If you say it's skinnier by 3, that doesn't make sense. But when it's a big number multiplied on the inside, it gets skinnier. When it's a fraction, it gets fatter. So just to be super clear, my normal square root graph looks like this. It has the point 4, 2. This one is skinnier by 2. Everything, it gets kind of pushed and pushed and pushed, kind of shrunken down like this. Instead of this being the point 4, 2, now it's only 2, 2. This point got squished, the whole function got pushed together in this direction until it became the point 2, 2 instead of 4, 2. Whereas in the other one, it got fatter. For this one, it got stretched way out to here, so now instead of the point 4, 2, it's all the way at 8, 2. I don't know if this is clear so far. Hopefully as I keep talking it gets clearer. So the general form, if we put together our shifts and our stretches, everything kind of looks like this. Where your options are, you could have a number multiplying on the outside. That would make it a vertical stretch by A. Multiplying the inside, that's a horizontal compression by B. Skinnier if B is a big number, fatter if B is a fraction. This shifts it right by H, up K, and that's true for all of them. So if I'm looking at this and I want to know what happened, I know I shifted right 1 and I shifted down 2. The new thing is this one, the 5. The 5's on the inside. Inside I'm thinking horizontal, right and left. And it's a big number. Right on the inside things tend to be kind of backwards. It's big number, so it actually gets skinnier. Skinnier by 5 or compressed by a factor of 5. We shift right by 1 to the right because this was a minus. And we shift down 2. Down because this was minus. By the way, shift, I could also say translate to the right by 1, translate down 2. Let's try another. Here, my 1/3 is on the outside. So I know that's going to be a vertical stretch or a vertical compression. In this case, it's a compression. It's going to get shorter. The whole graph is going to get shorter. Vertical compression by 1/3. We shift right 1. And we shift up 3. Let's do another. Oh, no, let's do one of these. This is right the backwards thing. Instead of giving me the equation asking for the transformations, here they give me transformations. So let's say I start out with greatest integer function, which I don't know how to type in this program, so I just wrote greatest integer function. And I translate it up to right 6 and expand vertically by a factor of 4. So I know I'm going to end up with something like this. G of x equals, I have an option to put a number here, a number multiplying here, a number added or subtracting here, a number added or subtracting here. The fact that it's up to means at the end of this equation I'm going to have a +2. The fact that it is to the right by 6 means I'm going to have a 6 here, and to move it right I need a -6. And the fact that it's doing expanding vertically by 4, vertically means it's going to be on the outside. That'll be my equation. In this one, I know my whole thing is going to look something like this. If I'm going to translate it down 8, that means I need a -8. If I'm going to compress it horizontally by a factor of 2, that sounds like it's making it skinnier by a factor of 2, a skinnier graph. But if you're on a quiz and you're like, ooh, do you want this skinnier or fatter? I can't tell because compressed by 2, compressed by a half, it does not, just ask me. If I want to make it skinnier, it would be a 2 here. A big number on the inside makes it skinnier. A big number on the outside would make it taller. Here we're describing again. My two things is I'm multiplying on the inside. So that's going to be a horizontal dilation. In this case, it's a fraction, so it's going to get fatter. Horizontal stretch or expand by a 1/4. And I have a -2, so we're going to shift, translate down 2. How about this one? So I know I've got two things going on. I've got this -5, and I've got this 2. The 2 to me makes me think that I'm going to do a vertical stretch. The -5 makes me think I'm doing shift right 5. The thing is, I also have this negative here, and how's that affecting things? Because really, it's not 2 times the square root, it's -2 times the square root. So really I'm doing a vertical stretch by -2. But what does that mean? How do I stretch something a negative amount? Let's see. So a regular stretch by 2 would mean that I would look something like, that's a stretch by 2. It was here. Instead of the point 1, 1, it now passes through 1, 2. Instead of the point 4, 2, it now passes through the point 4, 4. Everything got stretched by 2. But I don't want 2, I want negative. So actually, I'm going to move, all my y values are going to get multiplied by -2. Oh, it doesn't flip. Oh no, tragic. Let's see if I can do it this way. Well, oh well. Get that out of the way. What ends up happening is my graph looks like this. Can I draw it on the spot? This is so much pressure. There's so much pressure. Oh goodness. Oh god. Oh god. Oh god. Oh, that wasn't bad. The moral of the story, if you ignore my theatrics, is when we have a negative sign, it means we actually do a reflection. It's like we stretched a negative amount. We got it so much shorter and shorter and shorter until it went to the negative amount. Negative means we do a reflection in whatever direction matches that stretch. We're doing a vertical stretch here, so we're actually going to do a vertical reflection. We took this, we reflected it in the vertical, the up and down direction, and we ended up with this. let's see another one. So if I were describing the transformations, I would also say reflect vertically, or reflect over x-axis, over the x-axis, because that's how something flips, a vertical flip. Up becomes down, down becomes up. In this one, I am going to shift right 5 for sure. And I'm also going to do, well, here I don't have a number, I just have a negative. That's like a -1. -1 means it's not going to have any stretching to it, or shrinking, but the negative means it's going to do a reflection. This time it's on the inside, so it's going to do a horizontal reflection. Instead of the graph you see in purple, it's going to look like this, vaguely, but picture it not as wavy with an unsteady hand. It reflects horizontally. So I could say a horizontal reflection, or I could say reflect over the y-axis, because that's the axis that it flipped over as it did a horizontal reflection. Right became left, left became right, so it's horizontal, but it flips over the y-axis.